In example 1, you'll notice that this is the first time that we've seen vectors that are not at right angles to each other. We're going to have to handle this just a little bit differently than the previous examples. First of all, we have an aircraft that's flying on a heading of 330 degrees. So starting at north, we would travel all the way around 330 degrees, which leaves 30 degrees between the airplane vector and the true north direction. Then we have a wind blowing on a bearing of 85 degrees. So that's our angle between north and our wind bearing, which is 85 degrees. So the magnitude of this vector is 40 kilometers an hour. The magnitude of our plane vector, of our airplane, is 150 kilometers an hour. And we need to find the resultant of these two vectors. So let's start by drawing our two vectors outside of the Cartesian coordinate system. Here's our 40 kilometer vector. And here's our airplane going up like this. And we can still use the parallelogram law to find the resultant vector. The resultant vector is going to be somewhere in between these two vectors. And if we bring the airplane vector over and make a parallel vector with it, then we have 150 kilometers an hour. Down here we have 40 kilometers an hour. And here we have angle theta. What we're missing is our right angle. So in this case, we're going to be using the cosine law to find not only our resultant magnitude, but also our resultant angle. First thing we need to calculate is the angle here, and we can easily calculate that angle by going back to our original diagram and looking at the bearing that they gave us for the airplane. We know that it's 30 degrees between the north, or the y-axis, and the airplane. And so taking that back over to our diagram, we can quickly see that this angle here needs to be 60 degrees with the horizontal vector. Now remember the cosine law, a squared equals b squared plus c squared minus 2bc times the cosine of angle A. We're going to use this law in order to find our resultant. In this case, our resultant will be A, B can be 40, C can be 150, and the cosine of angle A is going to be represented by cosine of 60 degrees this time. If we work that out, then r squared is equal to 18,100. So r, the magnitude of our resultant vector, is approximately 134.5. So that's the magnitude of our resultant vector. Now we need to find the angle theta. Knowing the angle 60 degrees, and now that we know r, we have a matching pair with an angle and a side, and theta is also directly across from the side that we know, which is 150 kilometers. With that in mind, we can use the sine law to find out the value of angle theta. So we can say r over sine of 60 equals 150 over sine of theta. Now, r we just calculated at 134.5 over the sine of 60, which we know is 0.866, equals 150 over the sine of theta. A quick little way to find the value here is to use a little z pattern. We're going to go from the sine of theta, we're going to make a z, so we're going to take 0.8660 times 150 and divide by 134.5. So sine theta, rounded to 4 decimal places, is 0.9657. Using your inverse sine function on the calculator, we find out that the angle is approximately 75 degrees. So our resultant is 134.5 kilometers per hour, and the angle can be stated as a bearing of 015 degrees from north.